Today we are learning about derivatives. All right, let's start with some axes here. There's our y-axis. And let's have a function, just any old function. Let's have it look something like this. And we'll name a point here. We'll call this some x value. And then this would be the corresponding function value, f of x. And let's say we were to draw a line tangent to that point, to the graph at that point. So it might look something like this. So this is a tangent line right here in blue. So the question is, what is the slope of that tangent line? And the problem is that we don't know, because we know how to find slope if we have 2 points. And here we only have 1 point. So what we do is we just find a second point. So let's pick a point over here. And let's say that this distance from x to this point is h. That would make this x plus h, and then the corresponding y value, f of x plus h. Now if we draw a secant line through those 2 points, so this is our secant line, this is our tangent line, we would be able to find the slope of that secant line. So let's write that down somewhere, that the slope of the secant we know is change in y over change in x. So change in y, this distance here, over our change in x. So the change in y would be f of x plus h minus f of x. And that will be all over the change in x, which is x plus h minus x. And that will simplify in that denominator there. And we'll have just h in the denominator. And this here is the slope of the secant line, which we could argue is kind of close to the slope of this tangent line. But we can actually get the slope of the secant to be even closer to the slope of the tangent. We would just have to choose a point that's a little bit closer to our point of tangency, this x value here. So the smaller h is, the closer the slope of the secant will be to the slope of the tangent. So the question is, how small do we want h to be? And the answer is infinitely tiny. We want this distance here to be infinitely small. And the way we achieve that is with a limit. So we can say that the slope of that tangent line is equal to the slope of the secant, but we make h infinitely tiny. So here we have slope of the secant, which is this quotient of differences. So this is often called the difference quotient. And then we have the slope of the tangent, which is the limit of the difference quotient as h gets infinitely small. So here's an example problem. We want to find the slope of the graph of f at a given point. So we know that when we're being asked for the slope of a graph, that they really mean the slope of the line tangent to the graph at that point. And the way we find that is with the limit of our difference quotient. Okay, so now we're going to have a little bit of algebra. So we've got this is equal to the limit as h approaches 0, f of x plus h looks like this, minus f of x all over h. Now I'm going to distribute. And some terms cancel. Our 2x's are gone, our 3's are gone. And we're left with 2h over h, which is just 2. 2 is constant, so as h approaches 0, 2 is just 2. And what's kind of funny about this problem is that we found that the slope of this line is 2 using calculus, where we could have seen that up here all along. Now this point is really irrelevant because the slope of a linear function is constant. The slope of this function at any point will always be equal to 2. Okay, so same kind of question. We're finding the slope of the graph. So we're looking for the slope of the line tangent to f at these 2 points, at 0, 1, and at negative 1, 2. Now this is a quadratic function, so the slope will not be constant like we saw in the previous problem with a linear function. So we go about this the same exact way. So we have the limit as h approaches 0, f of x plus h, looks like that, minus the function we've got some cancellation, x squareds, 1s. So 2xh, h squared over h. We can take an h out of everything. So we get 2x plus h. So as h approaches 0, we want the limit of 2x plus h. So let's substitute. That gives us plain old 2x. Now notice that our slope has a variable, and that's because the slope of a quadratic will always be changing, unlike the linear function. So now we can find the slope at those 2 points. So the slope at the point 0, 1 would be 2 times 0, which is just 0. The slope at the point negative 1, 2 would be 2 times negative 1, which is negative 2. And so now we get to the actual definition of the derivative. Well, what's the derivative? That would be the slope of your tangent line, which we also have been referring to as the slope of our graph. So when we talk about a derivative, we're really talking about slope. So the definition of our derivative is just the limit of the difference quotient. And now there's a little notation for that. The derivative can be written as f prime of x or y prime, or sometimes we see it as dy dx. Now take a look. This looks like our slope formula, change in y over change in x, which makes sense because remember with derivatives we're talking about slope. And the other variation you might see involves brackets, so it's the derivative of y, like that. And here is our summary. We know that the definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h, and that the notation is either f prime, y prime, dy dx, or this version of dy dx. And we know that the derivative at a point is the same thing as the slope of the tangent at that point, or the slope of the graph at that point.